Okay, folks, we're almost done recording the stuff about science sections 1 and 2 that we didn't get to in class. Today we get to finish talking about the sun. This part is pretty fun. We're talking about stars, but specifically right now, the sun. So, the outermost layers of the sun are the photosphere, the chromosphere, and the corona. The photosphere is the visible layer of the sun. That's what you see when you are able to see the sun, which you're not supposed to look at directly, right? So there we go. Oh, why is this not working? Give me my highlighter. There we go. All right. The sun's interior resides within the photosphere. So here we have some kind of interesting pictures of the sun. Figure 2-13 is really boring in your resource guide, but if you can look online, it's kind of cool. So here's the photosphere, and here's the bulk of the sun, but there's all this other stuff, the corona out here, and then the chromosphere is this little layer right here that you can't see, or we can't see. All right, so going down to page 30, this is a fascinating thing that I had to point out. No known element can exist in a solid or liquid state at the temperatures at which the sun burns. So instead, the sun is composed of hot gases everywhere. There's no solid, there's no liquid. It's all gases or it's plasma. Plasma happens when electrons separate away from the ions. So remember when we were talking about the excitation of atoms and how their electrons move further and further away? When they actually separate from the atoms, that makes plasma. How cool, right? Nuclear fusion is the process that creates the sun's energy. Fascinating stuff. Creates lots and lots of energy. The sun rotates, kind of like Earth rotates, but not the same. It goes from west to east just like the sun. But here's the cool thing, it's not a solid body. Remember, it's all gases and plasma. There's no solids, no liquids in there. So depending on where you're at on the sun, different parts rotate at different speeds. This pattern, this weird rotation, they suspect that this is why so much of the violent activity happens on the sun. And now we're going to talk about some of the violence that is going on the sun. One of them is sunspots. Sunspots look like this. Sometimes using the right tools, you can actually see sunspots. But you should never look at them without the right tool. Fun fact, a typical sunspot is about 2 times the size of our whole planet. See why I geek out on this stuff? Super fun. All right, down on page 31, the number of sunspots. This is not constant, okay? Remember, we're talking about violence on the sun. Think of this as kind of like explosive volcanoes. The number of sunspots rises to a maximum and falls to a minimum in an approximately 11-year cycle known as the Sunspot Cycle. This is important to remember. There is a cycle wherein these sunspots go up to a high quantity of them on the sun and a lower quantity on the sun. Just remember that for now. Something called the solar activity cycle. The sun is most active with the greatest outbursts of energy and radiation for about 4.8 years. And during that 4.8 years of that cycle, there are more and more sunspots. Lots and lots of sunspots. So other things that are happening, all of that violence on the sun. Here's one that's called solar prominences. It's a form of solar activity and it's a fiery arch of ionized gas. It moves upward through the corona under the influence of the magnetic field. Then you've got a solar flare. It's a sudden explosive outburst of radiation from all parts of the spectrum and high velocity particles from the sun. So it's radiation and it's particles. Junk getting exploded out from the sun. Then a flare usually comes after the most energetic, most violent solar eruption, which is called a coronal mass ejection. plasma coming out from the corona. This is a picture of what a coronal mass ejection looks like. So it's shooting plasma out of the corona. Very cool. But yeah. Okay. This is something kind of fascinating. I always wondered how this worked, but I never really knew it. When electrically charged particles from the sun collide with particles in the Earth's atmosphere. So what's happening here, all this crap is coming off of the sun, okay? And it comes all the way to Earth. It makes it that far. So when that junk, that garbage from the sun is spewed out and lands in Earth's atmosphere, that causes our own atmosphere's atoms to get excited, okay? Remember, those atoms, or the electrons, are moving out further away from the nucleus during excitation. After that, they can become de-excited, which, if you remember, causes them to eject the little photons. This causes the phenomenon of aurora borealis, or the northern lights. And then there are the southern lights, aurora australis. So here's what happens. The oxygen atoms emit a pale green color. Nitrogen produces red-violet. Nitrogen ions emit blue-violet. This is happening as those photons are being emitted from the de-excitation of the electrons. Super cool, right? Unfortunately, we can't usually see them in Iowa, but if you're ever in the Arctic or Antarctic, you should try to check out the northern or southern lights. These often happen after a solar flare, because if you remember, it happens because of sun garbage being spewed out and hitting our atmosphere. All right, John Glenn, he has gone around the Earth. Very exciting. Read the postage stamp. Going back to the solar garbage coming into our atmosphere, all of that excitation is also causing ionization. These outbursts disrupt radio transmission. They disrupt navigation. It will also do things like disrupt the power grid. When I worked for Mid-American Energy, this is something I studied. The problem of what they called, I think they're called geomagnetic incidents. I might not have that exactly right, but it messes with the magnetic field of the globe of our Earth. So the NOAA Space Weather Prediction Center, they watch this stuff, and it's space weather. So you can be a space weather person. Sounds kind of fun to me. I think I would like that. All right, next we have solar wind. Solar wind is energetic electrically charged particles that flow outward from the sun. This happens all the time. Solar wind is constantly happening. Trust me, you do not want to be caught in a solar wind storm. Remember that cycle of sunspots? What did they call it? The solar activity cycle? Solar wind is most intense during periods when many sunspots are visible. Solar activity is at a maximum. We also get higher solar wind. All right, now we're going to talk some more about stars, not our sun. Life cycles of a star. Stellar evolution refers to the changes that stars undergo as they age. In other words, their life cycle. These changes can't be observed directly because they take place over millions and billions of years. Plus, remember that light travels to us. Even though it travels very, very quickly, what we are seeing from stars is actually quite old. Okay, a protostar. This is a star in its earliest observable phase of evolution. It's a little baby star. Fun stuff in this section, but what I want you to remember is that little baby star, as all of this energy is happening inside of it to create the star, the protostar here, its center is getting hotter and hotter and hotter. Kinetic energy, right? All of these atoms are moving faster and faster. When it gets to 10 million Kelvin, that's super hot, by the way, nuclear fusion reactions begin. Okay, so now the really exciting stuff happens. All of this is creating pressure. Eventually, all of that outward pressure balances the inward pull of gravity. We reach something called hydrostatic equilibrium. Once the protostar reaches hydrostatic equilibrium, it stops contracting and it radiates its own light. Now, dun, 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 you can say the star is born. The protostar becomes a newborn star. Okay, now remember the HR diagram and main sequence stars. Main sequence stars can be thought of as adults. Okay, so these are not protostars. They have already reached hydrostatic equilibrium. Okay, a star spends the majority of its life shining steadily. The luminosity and the temperature values are along the main sequence of the HR diagram. A main sequence star gets its energy from nuclear fusion. Okay, same thing that's happening inside the sun, nuclear fusion. Hydrogen, in this case, is at the center, being converted into helium. This is called the proton-proton chain reaction. This is fun here. 4 hydrogen nuclei become fused into one helium nucleus. Remember, mass cannot be created or destroyed, so it becomes energy. That energy lost from those protons is converted into energy and it's released. Okay, hence light. More about the space race here. We have Gemini, the Gemini program. Okay, going back to nuclear fusion and all of the energy coming out of our new stars. We're going to talk about Einstein now. The energy from these reactions eventually makes it from the center of the star to the surface. It's released via electromagnetic radiation. Remember the electromagnetic spectrum. Okay, so we're going to see a wave in some way, shape, or form, whether it's a gamma ray or a radio wave. The amount of energy released in one single nuclear fusion reaction comes from Albert Einstein's famous equation, E equals mc squared. E is energy released, m is a difference in mass before and after, c is the speed of light. That is how we measure the amount of energy released in a nuclear fusion reaction. All right. Now we're going to move on to kind of the miscellaneous things about stars. A supernova, large, violent explosion that takes place at the end of a star's life. So we talked about protostars, right? Those are new, like before it's even an actual star. Then they reach equilibrium and become baby stars. Now a supernova is at the end of its life. A type 1, okay, this is interesting. A type 1 supernova only happens in what are binary star systems. That's 2 stars orbiting the same point, okay? One of those stars, which is a white dwarf, pulls matter onto itself from its companion, right? Gravitational pull. Eventually, the white dwarf gets too much matter. As the white dwarf becomes more massive, the internal pressure required to support its weight increases. If the dwarf's mass exceeds the limit beyond which it can't maintain equilibrium, remember, static equilibrium, it will collapse inward and it will rapidly undergo carbon fusion before exploding. Super awesome. I would love to watch one of those. The second type of supernova is a type 2. This also happens at the end of a single star's lifetime. Type 1 was a binary system, right? It's pulling garbage from the other star. Type 2 is just one single star. It begins to expend the hydrogen in its core used to being converted to helium for fusion, right? So the core becomes more and more heavy. It keeps getting hotter. Eventually it can't withstand its own gravitational force and it collapses. When it collapses, it rebounds outward and you have a giant explosion. All right. After that explosion, it can collapse more and become a neutron star. They have very high or very strong magnetic fields. Here's a pulsar. It's a rapidly rotating, highly magnetic neutron star. So it's a type of neutron star. These were discovered by a lady at Cambridge, and her advisor took the Nobel Prize for it. Yay. Black holes, talked about right here. My time is about up. So read about black holes on your own.